We've just defined the electric potential in terms of the path integral of the electric field. This definition establishes an essential connection between the electric field and the electric potential. We can think of these quantities as being different encodings of all information necessary to describe a given electrostatic environment. How do we convert from one description to the other? The big idea is simply that if we can integrate the electric field to determine the electric potential, we can also do the inverse, which is to differentiate the electric potential to determine the electric field. We'll start with the example of the point charge fixed at the origin that we discussed in the last slide. Namely, choosing the zero of potential at R0 equal to infinity yields the simple expression for the potential, V of R is equal to KQ over R. Here we see a plot of this potential as a function of R, the distance from the point charge. We expect that the electric field produced by the point charge can be obtained from this expression by simply differentiating. In particular, we expect that E is equal to minus dV dr. When we differentiate the form for V of R, we do indeed get back the familiar result for the E field produced by a point charge, namely E is equal to KQ over R squared. To illustrate this result, we draw the slope at various values of R in the V of R versus R plot to create the plot of minus dV dr versus R as shown. Note that, for example, that if we compare the slope of the V of R versus R plot at R equals 1 to that at R equals 2, we see the slope has decreased by a factor of 4. Exactly the decrease expected for the electric field if R is increased by a factor of 2. When considering problems involving 2 or 3 dimensions, we need to differentiate the potential in 2 or 3 dimensions to yield all of the components of the electric field. This is called finding the gradient of the potential. A great way to visualize this, in the case of 2 dimensions, x and y, is to plot the magnitude of the electric potential in the 3rd dimension, z. The potential shown is just that of our example of a point charge located at the origin in the xy plane. As in the one-dimensional case, the steepness of the potential at any point tells us the magnitude of the electric field. But now that the slope at any point of the potential surface also has a direction, we obtain the direction of the field as well. The mathematical form of the gradient depends upon the coordinate system used. In Cartesian coordinates, the form of the gradient is what you might expect, namely the generalization of the one-dimensional expression. The gradient takes on a somewhat more complicated form in spherical and cylindrical coordinates, as shown.